the final case in this chapter is this periodicity. So the integram doesn't seem to have periodicity on the real axis, but we generalize the complex plane and it becomes periodic in some sense. So this is 10. And the integram is x divided by sinh. So this is a hyperbolic sine of x. And obviously, that at x equals 0, both the numerator and denominator are 0, but you can convince yourself this is a removable singularity. So there's not real singularity, that you can remove that singularity. So that integral is well defined. And at large x, sinh is exponentially large. So x divided exponentially large, so we will be 4 off fast enough. So this integram is well defined. Okay, and now this is a real, this is an even function because sinh is odd, and x is odd, obviously, and then the whole function is even. So the first thing you can do is introduce it, extend it to the total real axis. And if you like, you can use a principal part because you need to remove the removable singularity, but that either way is fine. But so the contour is like here, so we integrate along the real axis. You see, okay, that seems fine enough. All right, but what we'll use to solve this is using the fact that this sinh can becomes periodic on the complex plane. We can actually change that first to along the z-axis, along the on the complex plane, on the z-axis, on the real axis, right? Change this to that first, and then use the fact that the z is x plus I change, consider the along the complex number x plus y, and use the formula. You probably can learn that before, but it can also be derived in quite straightforward manner because z sine sinh c is right here. C is just 1/2 of e0 minus e minus e. And using this definition, you can divide this formula. This sinh a cos b s c b cos a. Right? Yeah. So that's the formula, and then now using a and b are x and high y. This is a. This is of b. This sinh of z is sinh of x cos of high y plus sinh of high y cos of x. Okay, now we use the fact that the in total imagined argument of cos and sinh are related to sine and cosine. We can figure that out because cos is that's the same. E to the z plus e to the minus z. So if the cos has pure imaginary, this become iy, this become minus iy, and this obviously become cosine. This become cosine 1. Cosine 1. Right? And for sinh, a slight complication become this is IY, this is minus IY. The sign is defined as 1 over 2I. So you just change the IY and minus IY. That means you need to divide it by I and multiply by I. So it's I times sine of I, sine of Y. Okay, and the way we try to do it is choose a Y value. So this is X, this is X, this is Y, right? You want to choose a Y value such that the sinh is back to just a sinh, or proportionate is just a sinh, right? And the obvious choice is so that sine Y is 0, right? You can say, you can choose either sine pi is 0, right? And cosine pi is -1. So that probably will work. So pi, there's a pi here. So you want to connect the real axis that you want to do, and with a path integral along y equals to pi. I think that the calculation is maybe because you can choose different paths. It's just the same, right? And then you can connect the two by adding extra line. This is a box with this location, you know, this location, whatever this value is, r tends to infinity. This is minus r tends to infinity, tends to negative infinity. So you introduce this two line at large x, at large absolute x value, and that will make the integral zero along this two line because sinh is large along this two line, and the integral backward from here to there is along y is pi, so this is -1, and you get exactly the sinh x here, and the imaginary part will be 0 along this path. All right, so now you can write down the residue stream according along this path. So some space. So you have original. This one is. I mean, let's consider this. I mean, this is just this because of the extra factor around. Just consider this one. So maybe this is called 1/2 I pi. I don't have a good name. So just consider this. Just integrate over this path. This I pi factor. All right. So I pi along the real axis is just this one. There's nothing singular along the real axis. So you can just the first part is I pi, and then plus this at this line is R, and then plus this, let's call this I sub 1. I sub 1 plus I at minus R at minus R equals the residue. Now we want to figure out the residue. Residue is when the integram is, I mean, the denominator is 0 because the numerator is z is analytic. So when will it be 0? And you see that it will be 0 at there actually no 0 here. The 0, the first 0 is sine y is 0. The imaginary part is 0, and the real part will be 0 only at x equals 0. So that's only the over this loop. The only pole is here. Yeah. So so that have to go past the singularity, and the way we can do it is just deform the loop either above it or below it. If we go above it, then the right hand side will have a residue. you go below it, then there's no singularity, that will be zero. That seems to be easier. You can go below it, right? So that means it's zero. And we argue that these two parts will not contribute. Well, now the argument is that this I, consider the I sub one. I sub one is now is integrate minus infinity. Z is at x plus longitude, and this is pi I, right? X is plus pi I, and then dx actually is from infinity to negative infinity, right? But we divided by the sin x multiplied by minus 1. The cosine y is minus 1. The numerator, denominator is this one. Okay. And now there's real part and imaginary part in this integral. The argument is that it looks like it hit the pole, but then if you first realize there's no singularity in this, you can just say you take the principal value. If you do the same thing here, this basically the loop, you stop a little bit before the pole and go around and resume at the same distance away. Then this part will cancel because of this is an odd function. So this part and this part, the imaginary part will cancel as long as you're not hitting the singularity. Okay, so the imaginary part of the integral cancel due to the symmetry. Right? Your odd function, you integrate over the equal part in the positive and minus x, so that will cancel. All right, and then the limit of this you can flip it back to minus infinity to infinity using the negative sign. So that is equal to negative of just minus infinity to infinity. That's with the. I actually should this I sub one. Actually, you have this I sub delta. I sub delta in here, going around the loop, right? Because that will avoid the singularity, and that so that you have the I sub delta. And now to obviously you see that this part is the same as this part. The I sub one, this part is the same as this part. So you have two of them, right? And now is the contribution from this one, from integrating this function along this little circle. But unfortunately, I'm out of time. I don't want to bump into Dr. Charlie. Well, maybe we'll finish up next time. Okay. But next time we will just evaluate this I sub delta. Just stop to remember what we are here. Just evaluate this I sub delta, and the final answer will be these two are the same, but you divide it by 2, so basically it's a negative of this I sub delta. Okay, that is what we'll do. Yeah. Denominator for I1 integral. Yeah. On the right hand side, you have I1 is equal to denominator. Is that sign us open -1 or the one above it? This one? This negative one. This is a negative fact. This is this one. Cosine y is -1. This is fact. This is factor. Okay. But I use this one in the sin here. So this is sin x, and then cosine y we choose as pi. So pi, cosine pi is -1. Okay. All right, so let me stop here and finish it next time. Okay. Many question? When I think, yeah.
Bottom right, you have R going to 0, that's supposed to be R going to infinity.
I'll go to close to infinity. Yeah, yeah. This one, pi. This is just along this line. This line is x plus pi y, but y treated as pi. Right? So this going to here because we have an x here. Here we have a z here. Right? Z is x plus I, y, z. Okay. All right. So last time we ran out of time and couldn't finish this example. With just the last step. So this is example 11.8. And you still remember it. So it's to calculate this integral x. And so I will repeat everything. The class video is on campus. If you forget the previous steps, just look back. So basically, the idea is to use the sinh function, which becomes periodic if you go to the complex plane to change x to z. Then we choose a contour along real x, real z, so along x, y, and then close it, form a closed loop at infinity, going back and back to negative infinity. But the integral when it's in the change x to z is not singular at origin. Actually, it's the removable singularity. You can actually integrate it over, and but it's singular at this. This is y equals to pi. So, if you imagine x, this is I pi. Okay. So there's the singularity. The last time we said that we can either go up or go down. I think the textbook go up or right? We could go down. It doesn't matter. It turns out to be the same. Okay. So the loop is we have this. So this is just half of the real axis, and this is even. So over the whole real axis is 2i. Just this I. And last time we argued that these two at infinity, the vertical lines integrals at 0 because sinh is large at the large argument. This two is at 0. When you go back, and we already argued that this sinh function, when y is pi, then it, the imaginary part is 0 because sine pi is 0, and that and it turns out that these two exactly the same when you integrate over the singularity. So there's two more I going back because there's the sign, although the sign of the integral is now infinity to back to negative infinity, but there's a cosine pi which is -1. So change the sign also. To last time what we missed is this little integral along this little circle with radius delta. So we need to integrate that along this pi, so we call it I delta. And when we choose going down, there's no more singularity within the loop, so that's 0. Okay, and now the idea is to what is left is to evaluate this I delta I sub delta is limit of delta goes to 0, and just doing the this integral. Okay, you know what I'm doing. Yeah. So what you need to do is it's slightly more complicated than what we did before because of the sin, but it's still straightforward. You follow the usual way of taking limits. So yeah, you just keep doing and don't panic. If you see something more complicated, okay. So this is z and this is dz, the z, and over here along the circle we can say this point, the pole is z equals to I pi, right? So along this loop, we can actually specify somewhere here. And this is z minus I pi equals to delta into the I theta, right? So that's how you describe this little circle. So that's equal going to here. So dz will be delta is fixed, so it's just I delta e to I theta e theta. Okay, and so and theta now you can choose like theta from start from 0 to negative pi or whatever you want to do. Right? Or if you like 2 pi back to pi, that's the same. You can say 0 to minus 3, right? And go backward, right? And now substitute everything. C is I pi plus delta e to I theta. Dz is I delta e to I theta d theta. Now the denominator, you just need to use the definition of sinh. 1/2 of e to the x becomes e to the z. Z is this one, so it's I pi plus delta e to the I theta, e to the z minus e to the minus z, right? Minus I pi minus delta e to the I theta. Okay, so that's how we do it. And now we eventually we take the delta go to 0 limit, but we can already drop some terms compare. So this is all the unit did is I pi. This is a delta, so you can drop this term compare with this one. So forget about that one. Right. And now the denominator, you have e to the I pi. The whole exponential function you can separate in the part in the product, e to the I pi times e to the delta e to the I theta, right? This is exponential function. Likewise, this becomes e to the minus I pi times e to the minus delta e to the I theta, right? And they have the factor in front of e to the I pi is just minus 1. E to the minus I pi is also minus 1, right? So e to the I pi is just this angle, so minus 1, e to the minus. So both have minus 1, so you can just take the minus sign out. Let me write one more line. 0. So there's a minus sign. Oh, there's a 2 over here. Yes. Or you can use the minus signs to change the limit. So minus pi, 0, right? And there's 2 I pi denominator. And keep everything. And the rest is e to the delta theta. But e to the delta e to the I theta, that's 2 exponential. Right? Then plus a minus because both have a minus sign coming out. Okay, now you use the property that when the argument, exponential function argument is small, you just do the Taylor expansion of the exponential function. Okay. 2 pi I. So now there's a negative sign, I times I minus 2 pi. And we'll take the Taylor expansion, just the linear term is delta e to the I theta. And this one, the linear term is, I mean, the first order term is 1, both have 1, but you have minus sign, 1 minus 1 is cancelled. So the 1 cancel. The linear term is delta e to the I theta minus of delta e to the I theta. So 2 delta e to the I theta. And then there's a delta square term, etc. Right? So now you can take the limit, delta goes 0, to drop all this term. And then delta and delta cancel. E to the I theta cancel e to the I theta. So altogether it's just minus 2 pi integrate minus pi to 0, which is pi, right? So that equates to minus 2 pi squared. Say it again? Oh, 2 cancel, yeah, that's a 2. Yeah. Minus pi squared. Yeah. All right. So that's I delta. So altogether is just right here. So 4I minus pi squared equals to 0. So I is equals to pi squared of 4. Okay, see if I come. Yeah, pi squared of 4. Yeah, your textbook going up. So if you choose to move up, they contain a residue. So you can, you want the right hand side becomes 2 pi I times the residue, right? But then you still need to subtract this part. So you still need to go through something like this part. And your textbook argued that if you go this part, this will be like half of the residue times 2 pi I. And that is fine because this is a simple pole. So which means our integration I sub delta is the negative of 2 pi I times residue divided by 2 because you integrate half of that. So that is fine for simple pole, but you just don't get confused. Don't just memorize this and then forget about the restriction. This is just for simple pole. If it's not simple pole, that doesn't work. Okay, if you go through half of that or a partial, a part of the circle, you just multiply the 2 pi I residue with the proportion to that part of the circle, just the fraction of 2 pi, that would be wrong. If it is not a simple pole, so it's a second order pole or higher order pole, essential singularity, those, no, it doesn't work. So you cannot do that. Okay, so you need to be careful. For simple pole, that's fine. So you just, turns out to be negative of pi I times residue. It's just the same. Do you know what I'm saying? That why 2 pi? Why is it? Why for higher order pole it didn't work? You cannot just divide the residue by 2, things like that. Do you understand that? Is because of what? Say it again.
Because the higher order terms will have the more terms without the 2, so you cannot just divide it by 2.
Very close. Because remember we derived the residue theorem, so like you have the Laurent series, right? So you have just like a Taylor series. Before that, you have A of 0 plus A minus 1 plus B minus 2, right? And then A minus 2, B minus. So you have a Laurent series expansion about the pole at C sub 0. So you have all these terms. If you integrate over the whole circle, then we already showed that quite elementary. We can show that all the integration of other terms, this term and that term, and all the higher different order term goes to 0 because of the periodicity of sine and cosine. You go over 2 pi, you always to 0. But if you're not integrating over 2 pi, you're integrating over partial circle, that doesn't work. Like this term, if you stop at second order pole, no higher order, no further negative infinity, negative power, then this one, if you integrate that over partial circle, this is not zero, right? You understand? You see that? Because we would like e to the I pi over this partial circle, and that might not be zero because the cosine theta and sine theta, that might not be zero. Okay, so you need to be a little careful about that.